Hello everyone, my name is Andrea. I am PhD student at PUC-Rio de Janeiro. I am presenting the preliminary results of my PhD, Mechanical Degradation of Polyacrylamide Solutions in Nanoparticle Suspension.
Polymer flooding is an enhanced oil recovery method that uses polymer solution to increase oil recovery by decreasing the water-oil mobility ratio by increasing the viscosity of the displacing water. The improved displacement of the oil is associated with an increase in the viscosity of the polymer solution. When flowing through porous media, the fluid is subjected to very high strain rates that lead to mechanical degradation. This irreversible process leads to the breakdown of polymer molecules and induces a loss of distribution of molecular weight related to a significant reduction in viscosity. So, it reduces the oil displacement efficiency. Here we can observe the behavior of the viscosity variation as a function of flow rate, experimentally measured using the Darcy law through a porous media. In the first region, we can recognize a shear rheology behavior, where the equivalent viscosity decreased due to increase in the shear rate. In this region, the flow is being dominated by the shear thinning effect. From a specific flow rate, the shear viscosity of the fluid continues to drop, but the extensional viscosity of the fluid begins to increase. Thickening effects dominate this region. After that extensional flow, the polymer reaches a critical point where a maximum viscosity is achieved, followed by a gradual decrease. This is due to mechanical degradation when the polymer chains are ruptured by the fluid acceleration field, lowering the molecular weight and the viscosity. To reduce the mechanical degradation in polymer flooding, nanotechnology could be used. Nanoparticles show unique properties due to their high surface area to volume ratio. The image on the left shows the interaction between the polymer and the nanoparticle, which is due to hydrogen cross-linking covalent bond. This interaction gives the material a more solid structure and a potentially better defined and stable shape. The graph on the right showed an example of the oil recovery factor versus the pore volume during the flooding process of water, polymer, and nanopolymer. Here we can see that the more significant oil recovery is for nanopolymer flooding than the two other flooding processes. This behavior cut we're interested in studying the impact of nanoparticles on the mechanical properties of degraded polymer solutions. To understand the influence of adding nanoparticles to a polymer, we want to study the behavior of the shear and extensional viscosity of the fluids. We started with the preparation of our polymeric and nanopolymeric solutions. Then, the solutions were characterized using rheology techniques to determine the shear viscosity and the extensional viscosity. For the mechanical degradation, we use a valve for flowing the solution at different flow rates to change the strain rate level of the fluid. The solution with the new properties were characterized by geometry. Finally, we compared the degraded and not degraded solution. In order to validate our experimental setup of degradation through a valve, we tested different flow rates with a polymer solution flow pump, commonly used in the oil industry. First, for the not degraded polymer, we observed that when the shear rate increased, the viscosity decreased, show a non-Newtonian behavior. This part of the viscosity curve is the shear thinning area where the polymer viscosity drops while the shear rate increases. It is important to note that for a high rate, the polymeric solution shows a constant viscosity behavior. Now, we are going to see the behavior of the polymeric solution at different flow rates applied. We could see that the viscosity doesn't change with flow rates of 1 and 2 milliliters per minute. it seems that it has no mechanical degradation with these flow rates. On the other hand, the shear viscosity drop at the low shear rate region with flow rates of 3 and 5 milliliters per minute. The percentage of loss of viscosity was around 30% for the flow of 5 milliliters per minute. This value was enough to study the influence of degradation on the viscosity of the solutions. When the flow rate increased to 6 milliliters per minute, the polymer behavior looks like a Newtonian fluid because the viscosity remains constant at the low and high shear rate regions. Moreover, this may be because the degradation of the polymer was almost total. We will now observe the extensional viscosity behavior of the degraded polymer solution and not degraded polymer solution with a flow rate of 5 milliliters per minute. The picture on the left shows the behavior of the capillary rupture extensional rheometry caver. The caver experiment is based on the creation of an unstable liquid bridge. After applying a stepped strain within a short strike time, the diameter of the liquid filament decreased due to the acting surface tension. Monitoring of the filament diameter as a function of time allows for determination of characteristic elongational flow properties, such as the apparent extensional viscosity. On the right graph, we can observe the extensional behavior of flow-upon solution. At low extensional rates, the elongational viscosity is constant. This extensional viscosity is equal to that of a Newtonian fluid. When the extensional rate increases, results in a strain hardening effect. A strain hardening effect can be explained as increasing material during a large strain deformation. The polymer degraded shows a slight drop in the viscosity, but the behavior is the same. Now, let's see the effect with the nanoparticles. Now, to understand the behavior of the addition of the nanoparticles, let's observe the result as a function of viscosity, as we did with the degraded polymer. Here, we can see that the viscosity of the not degraded solution of the polymer added with silica nanoparticles doesn't show any variation. It is also important to note that the shear viscosity behavior remains the same after degrading the solution. We can associate this effect with the interaction created between the polymer and the nanoparticle. As shown before, for the polymer solution, we will now study the behavior of the apparent extensional viscosity of our nanopolymer. So, to understand what happens in the extensional viscosity of our nanopolymeric solution, let us remember that the extensional viscosity of the polymer-only solution decreases for all applied strain. So, with the addition of nanoparticles, the apparent extensional viscosity increases for all degraded and not degraded solutions. Another important behavior is that the viscosity drop between the not degraded and degraded nanopolymer solution is lower at the two concentrations analyzed than the polymer-only solution viscosity drop. Finally, to summarize, we can observe that the nanoparticles in the polymer solution maintain the shear viscosity equal for the solution composed only of polymer. Moreover, after degradation, no significant alteration happened. On the other hand, the addition of nanoparticles modified the apparent extensional viscosity, increasing it. To conclude, it is crucial to recognize the effect of the addition of nanoparticles in the polymer solution on the increase of extensional viscosity. Another effect observed was the preservation of the shear viscosity behavior of the degraded and non degraded solution. The following steps to be performed in my PhD will be focused on studying the effect of various concentrations of nanoparticles. In addition, study polymers with different molecular weight, a variable that influences the viscosity of the solutions, and as final, apply all the studies performed at a microscopic level using a porous medium.